Welcome to the third session of this differentiation series. In this session, we will learn to evaluate limits using various algebra skills. In the meantime, we will also introduce the derivatives of exponential and logarithmic functions, along with the derivatives of 6 trigonometric functions through 8 worked examples. Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome to the series of differentiation, and this is the third session of this series. Example 1 is to find the limit of tangent x over x as x approaches 0. Since we have already known the limit of sine x over x as x approaches 0 equals 1 in the past video, the limit of tangent x over x as x approaches 0 is written to the limit of sine x over x times 1 over cosine x as x approaches 0. According to the product property of the limit, it can be written to the limit of sine x over x as x approaches 0 times the limit of 1 over cosine x as x approaches 0. Since the limit of sine x over x as x approaches 0 equals 1, and the limit of 1 over cosine x as x approaches 0 also equals 1, so the limit of tangent x over x as x approaches 0 equals 1. Here, example 2 is to evaluate 3 trigonometric limits. As for the first one, the limit of sine alpha x over sine beta x as x approaches 0 is written to the limit of sine alpha x over alpha x times beta x over sine beta x times alpha over beta as x approaches 0. According to the product property of the limit, it can be written to alpha over beta times the limit of sine alpha x over alpha x as x approaches 0 times the limit of beta x over sine beta x as x approaches 0. Since the limit of x over sine x equals 1, the limit of sine alpha x over sine beta x as x approaches 0 equals alpha over beta. As for the second question, according to the double angle formula of sine and cosine functions, we substitute cosine x by 1 minus 2 times the square of sine x over 2 and substitute the square of sine x by 4 times the square of sine x over 2 times the square of cosine x over 2. Hence, the limit in question 2 is simplified to the limit of 2 times the square of sine x over 2 over 4 times the product of the square of sine x over 2 and the square of cosine x over 2, which is simplified to 1 over 2. As for the last expression, since secant x plus tangent x can be written to 1 plus sine x all over cosine x, which can be further simplified to the square of cosine x over cosine x times 1 minus sine x, all in parentheses, after multiplying and dividing 1 minus sine x on both numerator and denominator. So the limit in question 3 is simplified to the limit of cosine x over 1 minus sine x as x approaches 3 pi over 2, which equals 0. Example 3 is to find the derivative of the function e to the x. Here we still use the first principle to find the derivative of this exponential function. So f prime of x equals the limit of f of x plus h minus f of x all over the step h as h approaches 0, which is written to the limit of e to the power of x plus h minus e to the x all over h as h approaches 0. Since e to the power of x plus h can be written to e to the x times e to the h, the derivative function is now written to e to the x times the limit of e to the h minus 1 all over h as h approaches 0. Now let's focus on the value of the limit e to the h minus 1 all over h as h approaches 0. We here assume the another variable y equals e to the h minus 1. Hence, h can be written to the natural logarithm of y plus 1. Now, after a few steps of simplification, the limit expression is transformed to the reciprocal of natural logarithm of the limit of y plus 1, or in parentheses to the 1 over y as h approaches 0. Since the limit of y plus 1, or in parentheses to the 1 over y as y approaches 0 equals e, the reciprocal of the natural logarithm of the limit of y plus 1, or in parentheses to the power of 1 over y equals the natural logarithm of e, which is 1. Hence, the derivative of the function e to the x equals itself. Example 4 is to find the derivative function of natural logarithm of x. Since y equals natural logarithm of x, e to the y equals x. Accordingly, dx by dy equals e to the y. Hence, dy by dx equals the reciprocal of dx by dy, which equals the reciprocal of e to the y, which equals 1 over x. Example 5 is to evaluate the limit of f of 5 minus h minus f of 5 all over 3h as h approaches 0, given that f prime of 5 equals 2. Since f prime of 5 equals 2, and based on the first principle, f prime of 5 is written to the limit of f of 5 minus h minus f of 5 all over negative 5, which equals 2. Hence, the limit of f of 5 minus h minus f of 5 all over 3h as h approaches 0 is written to negative 1/3 times the limit of f of 5 minus h minus f of 5 all over negative h as h approaches 0, which equals negative 2/3. So the limit of f of 5 minus h minus f of 5 all over 3h as h approaches 0 equals negative 2/3. Example 6 is to find the derivative of sine function. Here we still use the first principle to find its derivative function. Accordingly, the derivative function of sine equals the limit of sine x plus delta x minus sine x all over delta x as delta x approaches 0. According to the sine addition formula, sine x plus delta x is expanded to sine x cosine delta x plus cosine x sine delta x. Hence, the derivative function of sine x equals the limit of the ratio of cosine x sine delta x minus sine x times open bracket 1 minus cosine delta x close bracket, or to delta x as delta x approaches 0, which can be further simplified to cosine x times the limit of sine delta x over delta x as delta x approaches 0 minus sine x times the limit of 1 minus cosine delta x all over delta x as delta x approaches 0. As we have already demonstrated in the previous video, that the limit of sine delta x over delta x as delta x approaches 0 equals 1, and the limit of 1 minus cosine delta x over delta x as delta x approaches 0 equals 0. The derivative function of sine x is cosine x. Example 7 is to find the derivative of cosine function. As we did in the previous example, the first principle is still used here to find its derivative. So the derivative of cosine function is written to the limit of cosine x plus delta x minus cosine x all over delta x as delta x approaches 0. Since cosine x plus delta x can be expanded according to the cosine addition formula, the derivative of cosine x equals the limit of the ratio of cosine x cosine delta x minus sine x sine delta x minus cosine x all to delta x as delta x approaches 0, which is simplified by combining the like terms. Hence, the derivative equals cosine times the limit of cosine delta x minus 1 all over delta x as delta x approaches 0 minus sine x times the limit of sine delta x over delta x as delta x approaches 0. As mentioned in the previous example, the limit of cosine delta x minus 1 all over delta x as delta x approaches 0 equals 0, and the limit of sine delta x over delta x as delta x approaches 0 equals 1. The derivative of cosine x is negative sine x. Example 8 is to find the derivative of tangent function. According to the relation of trigonometric functions, the derivative of tangent x is transformed to the limit of cosine x sine x plus delta x minus sine x cosine x plus delta x all over the product of delta x, cosine x, and cosine x plus delta x. The details of the transformation you can read on the screen. After expanding sine x plus delta x and cosine x plus delta x on the numerator, we find the term of sine x cosine delta x shown in red are cancelled. Hence, the derivative expression is reorganized and simplified to the limit of sine delta x over delta x as delta x approaches 0 times the limit of the reciprocal of cosine x plus delta x as delta x approaches 0, which can be further simplified to the reciprocal of the square of cosine x. Here we continue to find the derivative function of tangent x, using the quotient rule as an alternative approach. According to the quotient rule, the derivative of tangent x equals the derivative of sine x times cosine x minus sine x times the derivative of cosine x all over the square of cosine x, which can be simplified to the square of cosine x plus the square of sine x all over the square of cosine x, which is the square of secant x. In the similar manner, we can find the derivative functions of cotangent x, secant x, and cosecant x as shown on the screen here. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.